So, swap over to here, and we'll just dive right into it. So this was a tracing problem, much like the page said it was going to be, where we were doing, again, two parts. This time we're dealing with some kind of more logic stuff. So we saw and, we saw ors, and we saw negation through the nots. Okay, so basically all three things you can possibly see. You're not going to see X or anything like that. So that's what these are designed to test. So let's go through. These are kind of important concepts. They're especially important in MATLAB. They're important in every single programming language. The programming is logic. And being able to do ands and ors and nots basically is what makes up programming as a whole. Somebody spent several years with the course here, discrete mathematics, that basically does nothing but logic with nots and ands and ors and XORs and stuff. So if you have questions, ask her. Much like questions about mesh scripts. So yeah, it's super, super important in programming in general, so it's super important that you get a grasp on it early. And in reality, it's not the most complex thing in the world once you understand what the rules are actually trying to say. If you don't know what they're trying to say, you get confused with them, it's super easy to screw something up, so it's important to sit down, think about what the rules actually mean, and go along with them. So there's truth tables that were in the lectures for sure that you can definitely go over. Those would be nice to bring to the exam, let's say. Okay, anyways, enough about that, let's actually go through this. So, starting with the one on the left, we start off with x is equal to 2 to 10 by steps of 2, which is going to give us 2, starting with 2, and then steps of 2, which gives us 4, 6, 8, ending with 10. Then we have y, which is 1 to 10 in steps of 2, which, very similar to what we just saw, is exactly the same except we start with 1. Okay, so those two steps should have been straightforward. Everyone should have gotten by this point in the review. Now we move on to the logic stuff a little bit harder. So, we have this line. So, everywhere in y where x is equal to 4 or x is equal to 8, set it equal to 0 is what that line is trying to say. This is a little bit difficult to digest all in one bite, so what we're going to do is break it down into its constituent parts. First of all, what we're going to do is pull this out. So, we have two parts here. X is equal to 4 and x is equal to 8. And these are ORed together. So, let's take a look at what x is equal to 4. X double equals 4. Let's take a look at what that vector, the logical vector, is going to look like. So what this means is everywhere in x where there is a 4, set it equal to 1, elsewise give it a 0. So looking here, so it's 0, 1, 0, 0, 0, 0, 1, 0, 0, 0. Okay? And the same goes for x is equal to 8. 0, 0, 0. Uh-oh. 0, 0, 0, 1, 0. Okay.
Because then you take the x.
So, we have all the places where x equals 4, all the places where x is equal to 8 as 1s. Okay? And now we need to apply the OR operation between them. And to make this a little bit easier, I'm going to move this over here. Because I can do that. Okay. And now with OR, basically any column that has a 1 in it, or 1's in both rows, becomes a 1. So we can just add them up. 0 plus 0 is 0, 0 plus 1 is 1, 0, 1, 0. Okay? So OR means either or can be 1. If they're both 0, it means it's still a 0. Okay? Again, refer to the truth tables for this if the rules don't make sense intuitively. After using them enough, they'll start making sense intuitively. So, what we're saying is put this logic matrix into y here. So, we're going to rewrite this as y of 0, 1, 0, 1, 0 is equal to 0, which means set y at all the places where there is a 1 in this vector equals to 0, which means that y becomes 1, 0, 5, 0, 9. Okay? Okay. So now we're going to move on to the next part. The next part is pretty much exactly the same, except now we're saying those places in x equal to 0. So we already have what this looks like. It looks like this right here. So we're going to use it on x now. Okay, that's the line that we're examining. which means that x is going to be equal to, yep, 2, 0, 6, 0, 10. Okay? So we had the values of y and we have the values for x. Now we have the last problem, which is a little bit tricky. Okay? So what we're going to do, again, let's write it out. X is x of x less than 6, and x is equal to y plus 1. Okay? So this is what our x looks like right here. So let's break this down into its parts again. And let's think about what the logical matrix looks like here. So x is x is less than 6. So everywhere that x is less than 6, we're going to put a 1. So 2 is less than 6, 0 is less than 6, 6 is not less than 6, 0 is less than 6, 10 is not less than 6. Okay? So we're looking here, and we're getting these values down here. Okay? Now we're going to do a little bit trickier one, which is x is equal to y plus 1. So, what we have to ask ourselves is the value of x at a given location equal to the value of y at that same location plus 1. So, we're going to go along, and we have both on the screen right here. We'll start at the 2. Is 2 equal to 1 plus 1? It is. Okay? Is 0 equal to 0 plus 1? No. Is 6 equal to 5 plus 1? It is. Is 0 equal to 0 plus 1? Not. Is 10 equal to 9 plus 1? It is. Okay. So, just like we did before, now we can just stack this right over here. Okay. And throw some connecting lines so it's a little easier to see. And now with and, both have to be true in order for the result to be a 1 true. So, what we get is 1 and 1 is true, 0 and 1 is false, 1 and 0 is false, 0 and 1 is false, and 1 and 0 is false. So we get just the 1 in the first position. And now we're going to use that to throw into here, and we're saying that x is equal, x of this is equal to 1, which means that x now equals 1, 0, 6, 0, 10. Okay? So, questions about this?